Greetings, this is Mark Anderson from Kellogg Community College, and in this statistics video we are going to look at hypothesis testing and comparing and contrasting z-tests versus p-tests. I have actually in the first part of this two-part video talked about z-tests, where we use the z-chart to figure out if a set of data is so far out of the norm that we can basically reject the fact that nothing's actually happening. So referring back to the video that you may have just seen, or part 1 of this part 2 video, we had a null and an alternative hypothesis. The null was saying, hey, nothing's actually happening. The alternative is saying, yes, something is happening because our data set is so far out of the normal for this. They're so far to the right or the left or in one of the two tails of the unit, the normal curve. We're just going to have to say that we're rejecting the null hypothesis. So in step 2, what we would do, and this is again covered in the previous video, is we're going to find the critical value. Now the critical value is created by looking at your z-chart and figuring out, based on your alpha, what zone or how wide your critical region will be and what your test value needs to be. And this is from a formula that we will use. What will this test value be to get into the critical region? Now step 4 was to draw a picture, and I'll give you an example of a right tail curve here. There is a critical value, or I'll just label it CV, and let's say you perform the test value from your formula sheet and you find out that this is right here, where this is 0 and you're well to the right of the critical value or just anywhere inside here, then you're going to reject the null hypothesis. If you found that your test value was actually not inside the shaded zone, then you would not reject the null hypothesis and say, yeah, there's, maybe nothing's happening here. But in this situation, you would definitely reject the null hypothesis. And then you would write a summary sentence that I've coached you through in the previous video. So how are things the same and how are things different in a p-test versus a z-test? Well, the null and alternative is exactly the same. You would still set up your null as being equal to a value, and your alternative would be greater than or less than or not equal to, based on whether the problem indicates it's left tail, right tail, or two tail. Now, instead of finding the critical value, what you're going to do is run the test value formula that you did in step number 3. So performing the test value will be actually pretty important, because what we have is the x bar minus mu divided by the standard deviation divided by the square root of n. And this is the test value that you'd use in step number 3 if you have more than 30 pieces of data. Now, for step 3, what you're going to do is you're going to look at the z-chart with this formula's number. Like, you are going to go to your z-chart, look at the z-chart, and then you're going to get the percentage. Get that 4-digit number from the z-chart by getting the test value and converting that to a percentage to see how much of the population is below that number. Then in step 4, instead of drawing a picture, you're going to have to process the p-value. Now, what I mean process is sometimes your percentage value needs a little modification based on what the problem is actually doing. Also, it depends on what tail it is. It depends on left tail, right tail versus two tail. And so I'm going to actually make a little chart for you to memorize, and it won't be on your formula sheet, so this is something you'll kind of have to keep in your head. You'll have to process this p-value and then write the summary about that. In previous videos, I've made the p-tests were always 5%, and now that we've gone from 8th edition to 9th edition to 10th edition and beyond in my class, the book doesn't always have to have an alpha of 5%, though in these examples it will be. We'll kind of process a little bit more as we go here, but I really want to talk about that chart for a moment. And this is a chart that's vitally important for you to solve the problem. I would strongly recommend that you copy this chart down and then come back to it, maybe in your notes, because I will not be able to, for the sake of YouTube resolution here, I will not be able to have this chart on the screen at the same time as I do this problem here. So let's do the chart for the p-test. So what this needs is I need let's see, a short line here, and then this about cutting that in half, and we're going to make that like so. And this is going to be the top of our table right here. This is going to be the number of tails we have. All right, and you can obviously have one or two tails. It doesn't matter whether it's right or left, but if you have one tail versus two tails, and when you actually process the problem after step number 3, so you're going to go to your z-chart and turn this into a percentage, you're going to see, is the percent under 50%? So if your percent is under, or if your decimal in this case is under this, or if your percent is under 50%, or your decimal is under 0.5000, the good thing is with a one-tail test, you do nothing and you just evaluate it. But if it's two tails, you're going to need to double it. You're going to need to double it because you're going to have a situation where, since the data is split on either side, you're going to want to double it to make sure that you're not just fudging the data. And we're going to actually do a two-tailed problem, so you'll get to see why that is the case. But what if the percentage is over 50%, or the decimal is over 0.50000? What you're going to do is, if it's a one-tailed problem, you're going to subtract it from 1. Because we're always going to evaluate our p-value from the percent that's closest to 0. Because really, a lot of these p-tests are either going to want you to have just an alpha of 1%, 5%, or 10%. So if you get a percentage over 50%, that just means that you got to take the complement of that to actually evaluate it. Now, if it's a two-tailed test, what you should do, and if it's a two-tail and it's over 50%, you're going to subtract from 1 again, and then you double it. And again, doubling is because since you have half the critical region on either side, you're going to want to double it to compensate for the fact that it is a two-tailed test. So you actually have less of a chance of getting inside the critical region, so to speak. So I really need you to copy this table. And again, I realize that this maybe should see decimal under 0.500, or it could say percentage under 50%, but you get the idea from that. Copy this table because I need to move this down a little bit further. Alright, so here's what we're going to do. So we're going to start off with this local newspaper that wants to test the claim that some in-state four-year colleges are greater than $4,700, maybe for a semester here. So what they did is they looked at 36 colleges, and they had an average of $5,950 with a standard deviation of $659. So what we're going to use is use the p-value method. Now, in this situation, I didn't give you an alpha, but let's give the alpha of 5%. Now, I would also say that your book is going to be very explicit about that, but in any situation when there is no p-value given, just default to 5%. So in the z-test, we're going to have a null hypothesis and an alternative, and this is going to be the same for the p-test. So you're going to start off with, hey, this is a local newspaper wanting to test to see if four-year colleges are greater than 5,700. That sounds like an alternative to me, because you're saying that, hey, you guys are definitely more expensive. And the null is like, no, guys, it's totally 5,700. Nothing wrong with 5,700 to call it. But look, they got 36 colleges. That's your N right there. 36 colleges that had an average of, so this is N right there, had an average of $5,950. There's your X bar. Now this 5,700, that's our mu, because that's what we kind of expect everyone to be. And the standard deviation here is $659. So for step 2, you are needing to find the critical value. Now the critical value from an alpha of 5%, and this being right tail, and we can tell it's right tail because of the greater than symbol, The right tail of this problem is then going to mean that the critical value is positive 1.65. So on a normal curve here, let me just draw this, at 1.65, which this being 0. At 1.65 here, this is our critical value, and everything to the right is shaded in. So if we find that using our test value here in step 3, if we do our test value and find out that we're greater than 1.65, we are definitely in the high part of the population. We're going to reject the null hypothesis that the local newspaper will win its claim that some four-year colleges are greater than 5,700. So let's run that formula. And again, the formula was our, oops, hold on. Make sure I got my notes in front of me here. We're going to take our 5,950 bucks, subtract 5,700, and divide that by 659 divided by the square root of the sample size. And if I do that correctly, what I get is an answer of 2.28. And that puts me, well, way over there at 2.28. So my test value is higher than my critical value. Therefore, since 1.65 is less than 2.28, you could have also said that the other way around, 2.28 is greater than 1.65, we will reject the null hypothesis. And we're going to reject the null hypothesis because, man, you know, it's just we have a data set that is so far out of the norm that the norm can't be right at all. The average can't be the new bar. That bar needs to get moved to the right because these 36 colleges were just way off the charts. So let's talk about the p-test variant. The p-test is essentially going to run the same way here and here. So we got null and alternative. So what we have is mu equals 5,700 and mu is greater than 5,700 here. Okay, so far so good. Now we're going to go to step 2. Step 2 is not going to find the critical value. Step 2 is going to run the test value. So it would be the 5,950 minus 5,700 divided by the 659 divided by square root of 36. And what this gives me is 2.28. Now, that step is the same as it is over here. So step 3 was to go turn this into a percentage. So what I need you to do is look at the z-chart. Okay, so look at the z-chart at 2.28. On our z-charts, 2.2 is on the left-hand side and the 0.08 is on the top. So if we look at 2.2 and the 0.08, and we look at that 4-digit number right here, what you get is you get a 4-digit number of 0.9887. So this is a right tail test. So we have a decimal that is now above 0.5000, or a percentage that's above 50%. So in step 4, what we're going to do is if we have a one-tail test, which this is a right tail test, it's one tail, and the percentage is above 50%, we're going to subtract from 1. So we subtract that decimal from 1, and now what we get is 0.0113. Okay, so this last part of the evaluation is we get to see, is this smaller than the alpha? And if it is smaller than the alpha, we will reject. If it's bigger than the alpha, we will not reject. And so, yes, this is 1.13%, changing the decimal to a percent. So since 1.13% is less than 5%, you also could have said, the other way around, you could have said 5% is greater than 1.13%, we will reject the null hypothesis. And the reason why we're rejecting the null hypothesis is because 1.13% is so small compared to 5%. This data set isn't just in the top, isn't just below the 95%, it's like in the top 2% here. It's so far outside of the norm. And I kind of thought this is going to fail. And the reason why I thought this is going to fail is that the bar was set at 5,700. And if you look at 5,950 with a standard deviation of $659, I mean, if you add 659 and subtract 659 from this value, you're nowhere close to the 5700. So this seemed like a pretty easy win for the college newspaper, or for this local newspaper. All right, this is the z-test and the p-test for a two-tail test. And the reason why this is a two-tail test is by looking at this problem, this gives you definitely enough tips to lean on that result, because it says a researcher, he claims that the average wind speed of a city is 8 miles an hour. That sounds like a null hypothesis to me. That sounds like he's making this claim, the certain city's 8 miles an hour, and this is what he did. He took a sample of 32 days and found that the average wind speed was 8.2 miles per hour with a standard deviation of 0.6 miles per hour. So there's our little sigma. I'll just circle that right there. And this is going to be our mu, or not our, excuse me, this is going to be our mu here, and this is going to be our x bar, because this is what he found after running the data. Now, with an alpha of 0.05, is there enough evidence to reject the claim? This right there is your definitely two-tail language. This is to say, would you reject it? And rejecting it is merely saying, hey, my mu, forgot my mu there, my mu is not equal to 8. So either the average is 8 or the average is not 8. This is two-tail. And in this two-tail test for z, what we would do is we would look up the critical value, and we would do that by looking at the alpha, which is 0.05, and that means we would look up on the chart at alpha divided by 2. So for the two-tailed test, don't forget to take your alpha and chop it in half. So this means your alpha is going to be 2.5%. So you're going to look up 0.0250, and you're going to look up 0.9750, and that means your z-score is going to be plus or minus 1.96. Now, on the normal curve here, we're going to have then two tails, and the tails are going to be at plus or minus 1.96 and negative 1.96 with 0 in the middle. So if we run our test value here, and our test value will be our 8.2 subtract our 8 divided by, in this case, the standard deviation is going to be 0.6 divided by the square root of the sample size, which is 32. So if we find that this is inside any of the shaded zones, then we're going to reject the null hypothesis. If we find it's not in the shaded zone, if it's in the white space, then we will not reject the null hypothesis. So we do the calculations, and we type that into the calculator, and we find out it's 1.89. So sorry guys, it just missed the mark there at 1.89. It is not in the critical region. So since try to make that look more like since 1.89 is less than 1.96, or you could have also said that the other way around, we will not reject the null hypothesis. We will not reject the null hypothesis. On the p-test side of things, we should get through all 5 steps and also not reject the null hypothesis. But it will take a little bit of time to show you the difference, because we are not going to be comparing the z-test to the z-score. We're going to compare the percentage to percentage. So this is mu is equal to 8, mu is not equal to 8. And in step 2, we would run the test, which gives us a z-score of 1.89. Then we look at the chart to see what decimal that is. If we look at 1.89 on the chart, what this gives us is a decimal or percentage of 97.06, or 9,706 ten-thousandths. So this is what you find on the chart, and now we have to think back when we process this, what are we going to do? Well, this is two-tail, which means that we need to subtract this from 1. So we're going to go 1 minus 0.9706, and then we need to double it. And the reason why we need to double it is because when we take an alpha and cut it in half, we have to take our percentage and double it to compensate for the fact that we have smaller critical regions in this problem. Now, in doing so here, this is going to give us a decimal of 588 ten-thousandths, or a percentage of 5.88%. So how close is that to 5%? Well, it's really, really close. But unfortunately, close is not good enough, because we found that since the 5.88% is greater than 5%, and to reject the null hypothesis, we would need to be under that. We are not going to reject the null hypothesis. We will not reject the null hypothesis. Because when we do a p-test, we compare the percentages of the alpha to what we found on our z-chart. And this was bigger than 5%, so that means our data set, if you look back at this picture here, was not inside of the critical region. It was not far out enough for us to say that the average is wrong. Like we are not sure that we're making a type 1, we could be making a type 1 error here. So in this situation, we're not going to reject the null hypothesis. So the p-test versus z-test switches the order around. It has you look up the percentage and then process the percentage based on what I told you to do. The percentage is always going to be compared versus the alpha, so now you see the reason why we subtracted from 1. But again, on two-tailed tests, you do have to double it. So maybe think of it this way. On the one-tailed test, we would multiply it by 1. Well, on the two-tailed test, we'll multiply it by 2. So that is a good way to maybe compartmentalize it, because you're not going to have a chart like that on the test. You will have a z-chart, you will have a basic formula sheet, but you'll not have all these notes to kind of supplement this. That's what the homework's for. So give yourself some time with the homework so you don't have to really think too hard about the process here, because I'll have a formula sheet for you. That formula sheet will be one that you can bring into the test with you, and you can bring notes and just bring your graphing calculator to do some of these calculations here. Well, thank you for watching. This has been me looking at P versus Z, and I hope this with the Z-test video has got you on the good start here. So feel free to email me questions in class and let me know what questions you have after getting into the homework. Thank you for watching.